What we're going to do is we're going to look at how we do our VSEPR diagrams and then relate them, or the shape of the molecule, into the intermolecular forces that it can form. Now when we do these, remember the first thing we need to do is we need our Lewis structure. Then from our Lewis structure we can get our AXE formula, and from there we can then draw its shape and then look at bonds to determine whether or not it's a polar molecule or not. Okay, so we'll start off with our sulfur tetrachloride, and so the first thing we need is our Lewis structure. Okay, so now we have our Lewis structure. We can see that if A represents my central atom, I have 1, 2, 4 bonds, and I have 1 lone pair. So this is really similar to having 5 electron groups around our central atom, except one of them is replaced with a lone pair. If we have 5 electron groups, we know that it would be a trigonal bipyramidal. If we had 5 bonds, one of them is going to be replaced with a lone pair, and it'll be in the plane so that it gets the maximum separation. And so as a result, it's our seesaw shape. So now when we go down to draw it, we'll make our sulfur our central atom. I might have chlorine here, chlorine here. These would have been the 2 that are above or below the plane. And then I have my other 2 that would have been in the plane. Okay, and so the bond angle between these 2 is going to be less than 120 degrees because they start off 120 and they'll be pushed closer together. The bond angle here or here is going to be less than 90 degrees because that's what they start out as, and they'll be pushed closer together. Now, if I want to know what kind of intermolecular forces this will have, I first need to determine the nature of the sulfur-chlorine bond. So if I look up the electronegativities of sulfur, it's 2.5, and chlorine is 3.0. This gives me an electronegativity difference of 0.5. Since 0.5 is our cutoff to just being polar, I do have slightly polar bonds. And so, as a result, my electrons will be pulled that way slightly. These electrons will be pulled that way slightly. These will be pulled that way. So as a result, I see that I have a net pull away from the sulfur. And so this will give me a general overall dipole moment of approximately that. And so I can tell, therefore, based on its Lewis structure, that this has a seesaw shape. When I look at its shape with my polar bonds, I can see that it has a dipole moment. And so therefore, I would say that the intermolecular forces that this molecule can form would be London force and dipole-dipole. Okay, so let's take a look at a second one. And for this one, we're going to look at SF5 minus. So again, my first step is to get my Lewis structure. Okay, so now for my Lewis structure, I can see that I have on my central atom 1, 2, 3, 4, 5 bonds, and I have 1 lone pair on my central atom. Okay, so just like before, we know that this is similar to AX6, and that would be my octahedral, where I have my central atom. But one of them is going to be replaced with a lone pair, and so as a result, we have our square-based pyramidal. So now that I know my shape, I can draw it. So I'm going to have my sulfur in the center. I'm going to have a fluorine coming out of the page, going into the page. And for this, I know that all of my bond angles are going to be slightly less than 90 degrees because they're being pushed together by the lone pair that occupies a final position around it. Now again, if I want to know what type of, whether or not it is a polar molecule or not, I'd have to look up the electronegativities for sulfur. 2.5 for fluorine. This gives me a delta En of 1.5. So therefore I know that all of these bonds are polar. And they're going to pull towards the fluorine because it is the more electronegative. And so this will give me an overall net polarity of approximately that. And so therefore it's going to be London force and dipole-dipole interactions. Okay, let's take a look at one final one. Again, the first thing we need to know our Lewis structure. Okay, so from this Lewis structure, what we can see is that we actually have three central atoms. We have one central atom there, we have one there, and we have one there. And each of these central atoms have a different AXE formula. This one has an AX4, so therefore we know it's going to be tetrahedral around that one. This one has an AX3 because since double bonds lie right on top of each other, we treat them as one bonding group. So I have 1, 2, 3 bonding groups. So that's going to be trigonal planar. And then this one right here, I have AX2, E2. And so it's going to be bent. So now that I know its shape around each of them, I can go and add the bonds. So now, because I know with this carbon, I get 2 of the atoms on the page, and this carbon is going to have other things bonded to it, I want to make sure that it goes on the page. So therefore, I'm going to put one carbon there, I'll put my other carbon there, then 2 hydrogens. And so there's the 2 that are on the page for my tetrahedral. And then I have one coming out of the page, and one going into the page. And then I know that this has a bond angle. Okay, now this carbon, because we put it on the page so that it makes it easier to do my trigonal planar shape around it, which I know has a bond angle of 120 degrees. And then I can also show my bent, which has a bond angle of, in this case, about 105 degrees. Okay. Now I can go through and I can add my polar bonds. I know that my carbon-hydrogen bond is nonpolar because it has a delta En of less than 0.5. I can look at my carbon-oxygen. Oxygen is 3.5, carbon is 2.5. Polar bond is going to go like that. I'm going to have a polar bond that goes like that. And I'm going to have a polar bond between my oxygen and hydrogen in there. And so therefore I have that around this oxygen, and maybe something like that for that oxygen. So as a result, I know that this is a polar molecule where I have my London force, I have my dipole-dipole, and now this is where we have to analyze our structure. Since I have a hydrogen bonded to an oxygen, this hydrogen is able to form hydrogen bonds with other molecules. And then because I have oxygens with lone pair electron, I can also receive hydrogen bonds. So therefore this molecule with itself can form two-way hydrogen bonding. And it could also form hydrogen bonds with the other molecules and receive it. So it could form two-way hydrogen bonds.